Welcome to this webinar. It's hosted by Protech. My name is Anders Brask, and I am the CEO of Protech. Today's webinar has the topic Getting Started with Metal 3D Printing in Higher Education. And we have a guest, Andrei-Alexandru Popa, and he is the assistant professor at the Southern University of Denmark and also an Xact Metal user. Some quick information about the webinar. It will be recorded, so you would have a chance to look at it later and share it with your colleagues. The audience will be muted. You can use the chat section to ask questions during the webinar. Just type it in. You will find the chat section above in the upper end of your screen. If you prefer to ask questions directly to our team during the Q&A section, which will be in the end, please raise your hand and you will see the hand in your upper screen also, and you will be unmuted to ask your questions. The agenda for the day will be a presentation done by me for presenting Protech. Then we will have a short presentation of Xact Metal. Unfortunately, Xact Metal seems to have some connection problems, so I will do the presentation of Xact Metal. Then we will go over to the main topic of this webinar, and it will be an interview with Andrei, and it will be conducted by Thomas Tennyson, the sales manager of Protech. After the interview, I will do a short presentation of the local sales team in the Nordics for Protech, and we will go over to the Q&A section and end with that. Next, please. Just a short presentation of Protech. The company was founded in 1993, so we've been active for 31 years. Selling 3D printers, sold our first in 1994, so we're one of the oldest ones in the 3D printer game. We have a turnover of 10 million euro, roughly about 100 million Swedish krona. We are 30 employees, 20 whom are working directly with 3D printing. We have 2 offices in Sweden, one in Denmark, one in Finland, and one in Norway. And we are the largest professional 3D printer solution provider in the Nordics. The products that we work with is the Stratasys 3D printer brands, Ultimaker 3D printers, and obviously what we're going to talk about today, Xact Metal 3D printers, and Shining 3D scanners. That's the companies we're working with. Next, please. So a short presentation of Xact Metal. They have a mission, and that is to establish a new level of price and performance in metal 3D printing. And you will hear some of these examples of what Xact Metal actually means by price and performance. So also their exceptionally flexible view of openness in terms of what you use your printer for and the possibilities to work with parameters in the printer. Could I have the next slide, please? It's a young company, Xact Metal. They started in March 2017, introduced their first gantry-based printer XM200C in November 2017, and started to work and sell their printers in 2018, 2019 in the US. CE marked their printer and found their first sales partner in Europe in March 2019. The first sales partner is Protech. Today, they are working with 27 European sales partners and a wide network of partners throughout EMEA or in other regions, Asia, Pacific, and obviously the United States. The company is an American company. It's based with their headquarters in State College, Pennsylvania, in the United States. A couple of years into the 2020th, they introduced the XM200D, which is a galvanometric controlled 3D printer and started to ship that in July 2022. And one of the first ones actually went to the Southern University of Denmark, which we'll hear a lot more about later. And by ending 2023 June, they've sold 100. The 100th printer was sold, and by end of 2023, they delivered over 150 printers. Next, please. Okay, I will now handle it over to Thomas, and he can start the interview with Andrei. Thomas.
Thank you, Anders. Good afternoon. My name is Thomas Tønnesen. I'm the sales manager at Protech. I'm very happy to introduce Andrei-Alexandru Popa, assistant professor at the University of Southern Denmark, with who I'm going to talk about their experiences with the Xact Metal 3D printers in an educational setup. Welcome, Andrei.
Thank you, Thomas, and hello to everyone. This is a very fun little opportunity for us to present a bit of our work and the great collaboration I think we have with both Protech and Xact Metal. So yeah, looking forward to it.
Then let's jump right into it, Andrei.
Sure.
How did you first become interested in metal 3D printing?
Yeah, so my interest in 3D printing in general stems back from my PhD days. I'm a mechatronics engineer by trade. My PhD was done in polymer 3D printing, particularly in integrated wearables with sensing. We quickly found that while we were quite happy with our capabilities within polymers, the next natural step was to expand towards metals to cover a larger portfolio of materials, especially with the establishing of our new Center for Industrial Mechanics back in 2019. So that's a little bit of the backstory to this.
Interesting, thank you. So why did you choose to adopt powder bed fusion technology opposed to all the other metal 3D printing technologies?
Yeah, that's a very good question, and a lot of resources went into this decision at the time, I can tell you. Obviously, there are many ways of printing metal, and they each have their drawbacks and advantages. We looked a lot into the cost-efficient ones, for example, sintering metals, but we quickly found that we are a research center, we do educational activities, we do commercial activities, but we don't want to have a high throughput. What's essential for us is that we can really do complex geometries and tune them to do our bidding, basically. In this regard, literature suggests, along with the great dialogue we had with Protech, that laser powder bed fusion, or SLM, or DMLS, whatever you want to call it, yields the best results in terms of dimensional accuracy and overall part performance. So it's also a very well-established technology, which for us really meant that we didn't have to go blindly in the dark for quite too long. So that's why we went for this.
Great. What were your major concerns as you began exploring purchasing options, and how did Protech and Xact Metal address these concerns?
Yeah, I mean, I can also divulge that part of the dialogue with Protech was on acquiring a metal sintering system at the time. And my concern obviously was not to, break the budget on this. And that has a couple of implications, right? Because one thing is the acquisition cost of the machine. The other one is the cost to run it. There are many systems on the market that could make sense financially, let's say, even for a place like us at the time that did not have experience within metal. But what really, really struck us was that you don't need to put 200 kilograms of metal into this machine to even get it started, right? So the running cost was something that we didn't want to get buried in. And we quickly understood from the great support by Xact Metal and Protech on describing the technology and getting a live demo of how it is to use the machine, not just the stuff they would put on the website, right? They actually gave us a tailored view on this. We felt confident that this would not break our budget, and yeah, it has turned out that it has not. So good on us, I guess.
Thank you. So how would you describe the implementation process of the print into your facility?
Yeah, so I've recently bought some IKEA furniture back home, which took a little bit longer to install than the Xact Metal did at the time, potentially because I'm very bad at it. But to return a little bit to the previous question, perhaps the cost associated to running the machine is one thing, but also the cost to establish the environment around the machine can really be a deal breaker. So for us, this was nothing else than acquiring at the time the 200C, bringing it into the room, making sure that it has enough space around it, and that we have a little bit of a clear desk space where we can handle the powder. So we of course wanted to make sure we follow all the safety recommendations listed by Xact Metal. So we have all the proprietary and the recommended personal protective equipment. We have all the sieving stations. We have all the stuff that needs to really ensure you have a streamlined experience with the machine, and there's no risk. But this does not mean that you have to change your facility by installing pumps or blowers or, vacuuming out the area and having a separate entity for all this. So this was, I dare say, it was bringing the machine into the room, connecting it to power, and making sure there's not weird stuff around it.
I think actually that punctures some of the myth around metal 3D printing. So it's great to hear.
Yes.
How difficult was it to learn the machine operation process?
Yeah, so having what we thought, and we probably still do, having quite this vast experience within polymers, we quickly found out that metal 3D printing is not as much 3D printing as it is metallurgy. So that sort of, pushed us into uncharted waters, which naturally had a learning curve to it. This learning curve was far sweetened by the fact that not only were we handheld at the beginning by Xact Metal and Protech with their technicians here, and Xact Metal with their knowledge providers remote, but also we even got staff. We have Eli basically from Xact Metal visiting us a couple of months after the installation and sitting down with us for a full day, including some students that were interested in this and giving us a full blowout of how you can use this machine in, I dare say, less orthodox ways, which we are still very, very happy about today. So yeah, there is a learning curve to it. It's not the same kind of practice you would have. Maybe it's a bit similar to SLA because it's also a laser-based system. So there's some thermals to consider and whatnot. But in the end, I mean, it's nothing that will not make sense. And again, the support we got on this was vital to make us hit the ground running.
Great. Can you give a short overview of the work in material development? I know we've been talking about open parameters and so on. What role did the open parameter package have in this work?
Oh, I mean, without the open parameter package, I don't think we would have been very interested in doing metal 3D printing as a research institution. So we like to tinker, we like to experiment things, and we don't really like to take things as they are without challenging them, right? So while Xact Metal does provide you with support parameters, and they provide you with basically all you need to get started without thinking too much, we wanted to optimize these even further, not necessarily optimize, but rather tailor towards specific applications. And if you would help me a little bit with the slides, I think I can give you a nice example of how we have used this, or we have leveraged open parameters towards printing very cool stuff, I believe. So yeah, just to recap, we got this machine just during COVID. So we were still, we had machine number 37, serial number 37, I remember on this, so still a rather new machine, the XM200C. It was a gantry-based system. It had a 200-watt Ytterbium laser, and it's basically 5 cubic inches in this. So we got the machine, great, but what should we use it for? So on the next slide, you can see an example of one of the very first things we ended up printing. This work is done by my tremendously talented colleague, Joe Alexanderson, who is an expert within topology optimization. What you're seeing there, this coral structure, is actually a topology optimized heatsink. So it's a mathematically generated structure that is intended to dissipate heat from a computer chip. If you see the little rectangle it stems from. In the next diagram, you can actually see that the more heat you want to dissipate, basically the more of these antlers or dendrites or whatever you want to call them will grow, right? So excellent. There's a lot of heavy math behind this. I'm not going to bore you with it. What we did was, of course, bring it to life. And you can see that on the next slide. So we took the model that Joe had, and he had printed it in plastic before, but the plastic heatsink is boring, obviously. We managed to slice it and prepare it, unpack it, and do the entire workflow to get a metal 3D printed heatsink. And yeah, it looks a bit silly maybe, and we didn't do all the border parameters properly, but this image is very dear to me. It's one of the very first things we printed in steel, and yeah, it holds a very dear place in my heart. However, printing a heatsink in steel, you might argue, is not exactly efficient. So we moved to another material, if you can help me on the next slide, which was, of course, copper. And what you're seeing there is the same shape, just printed on a much smaller scale. It's small enough, if you look in the lower right corner of your screen, to fit within a ring that's sat on my, well, I think it was my right hand, so one of my fingers, for around 3 days. And yes, I did get skin poisoning from the copper, but I regret nothing because I had a copper ring. So, everything is good. Now, on the next slide, on the next image, actually, you will see that while the steel heatsink is around 60 millimeters across, this one is roughly 10. And I would love to say that we made it so small because we wanted to make it so small. It's actually the other way around. So we only printed it in this size because that's all we could do. Copper is a very reflective material. We had copper, chromium, zirconium, so it's a copper alloy. But it still comes with a lot of challenges. And literature suggests, and the dialogue with Xact Metal also confirmed this, you basically need either more power or you need a different wavelength for the laser. Different wavelength for the laser we couldn't get, but more power we could indeed. And on the next slide, you can see that we upgraded our machine into a swap deal, which I'm still very grateful for. So thank you, Anders. We upgraded to the XM200G. We were among the first places in the world to get this. So we got it about 3-4 months after they started shipping it out. It has a slightly bigger build volume, but what's interesting is the 400-watt white terbium laser together with the galvo setup. So this meant that in the next picture, you can see the progress from basically a third of this coral working to the full-blown shape, 60 millimeters across, and now we can have an actual copper heatsink. So how cool is that, right? We just got a bigger machine and it works. Now, of course, it's not that simple. We had to optimize parameters for it and whatnot. But in the end of the day, we managed to get this thing made, which is a great success story for me. If you go further, I can highlight an even more impressive, to me, example of the open powder capacities on this machine. There's a company in Canada. There are very good friends at Equispheres. They create non-explosible aluminum. Aluminum is a reactive metal, the same as titanium. You would need an 8X accreditation for your laboratory, again, entering this discussion with how much does it cost to integrate additive manufacturing in metal into your facilities. This powder is less explosible than the equivalent steel one. So we didn't need to extend our facilities to accommodate for this. And by the way, fixing your facility to accommodate for an 8X accreditation can cost double the amount of the printer sometimes. So we were very happy to find this. The problem is the powder is optimized for, well, not 400 watts, but 700 watts, meaning that we had to make our own parameters. And you can see on the top left picture, we have these little cubes, we have the dog bones, so we tested for continuity, we tested for delamination, we tested for density and all this. We have a full-fledged laboratory for this. So in the end, we found parameters on this machine that was not intended for this powder, nor has this powder been intended for this machine, to actually create the same heatsink that you saw already in steel and copper. And we've done the same for Inconel and other alloys. Yeah, if you go on the next slide, though, I can also tell you that part of the activities we do here involve commercial orders. So sometimes we get asked for polymers, sometimes we get asked for metals. We also develop and design for additive manufacturing. But once in a while, we get these very weird requests, which you can show on the next picture, please. So this is a copper benchmark piece, and it is close to being the full size of the build plate. It's optimized in the sense that it's tricky to print. It has overhangs, it has free supported surfaces, it has very thick walls, it has chamfers, it has all the bad things you never want to have. So this is basically something to stress test our device. And it had been printed in steel. It had not been printed in this size in copper. So we were tasked to do it. And well, the first thing we did was we developed some parameters for it. So on the next slide, you can see that we basically quickly reached, well, quickly, I have a postdoc that might disagree, but I think quickly enough, we reached 99.1617% density, and we thought for a benchmark, this is completely fine. The next thing was, once we found out the parameters in terms of scanning speed, lasers, and laser power, hatch distance, and so on, we had to figure out the strategy. So on the next slide, you can see that typically, you go from the strategy for the solid body, you consider the support type. So what structure do you want to support these free hanging surfaces? Then you have a strategy for the support, and then the layer height, so the distance between layers. And normally you just go, straight through this, but for this part, we quickly found in the next click that this is a very iterative process. And it took us a lot of, iterations before we managed to get to it. So in the next click, you can see that we made a table of what works and what we think works and what not. And on the next slide, again, you can see we tried a variation of very many things, including the one that finally worked, which is not supposed to work, which I think is just tremendous. So we basically scanned or double scanned the solid, and we scanned the support structure every second layer. So that's not even supposed to work in that way. But we were, at this point, we were willing to try anything because we were not going to let this thing not be printed, right? So one fateful Saturday at 3 a.m., we had this idea, and lo and behold, on the next slide, you can actually see that we managed to print this chunk of copper. And I am still super impressed by it to this day. So returning to your question, Thomas, without the open powder parameters, we would not have been able to make this. It's as simple as that.
And to those who sits out there and think, being all the parameter tweaking, it is for Andrei, who is very interested in tweaking and turning and new materials. But if you just want to print, there's already fixed parameters for known materials. So it's a both side thing. And now we've heard all about all these very interesting cases you've had. But as with all other technical equipment, you can enter into issues. Can you describe a time when you required assistance with your printer and the support provided to you from Protech and Xact?
Yeah, I mean, we can probably talk until tomorrow to give you such cases. I mean, as you know, Thomas, we have a quite active dialogue, me and you. Yeah. One example was that, as Anders mentioned, we got the XM200C also quite early in the development, and so did we with the G. And we just thought, as users, we should give feedback to the manufacturer, right? So we talked directly to Xact Metal about some considerations we had on the recoding. So the type of bearings that were used, we asked, could we replace them ourselves? And they said, well, what do you recommend we do? And we actually sparred with them. We found a solution, and they implemented it. They also shipped it to us directly and retrofitted and modified the thing based on this. So it's really a dialogue relationship we have on this. Other times we needed to install, I mean, we put GoPros inside this machine. We have, changed the pulleys. We have done all kinds of things you're not really supposed to do, but not only do they allow you to do it, they even help you do it, right? So we had the guys from Protech down here, Johan, who I'm sure is in the participant list, has been down here a couple of times, at least a year, to help us change some things. We have a new gantry, so we have not new gantry, sorry, we have a new optics setup. We swap in between and all this. So I mean, we give them challenges, and they seem to be up to them. So
I think it's a thing where both sides benefits from. So we are really happy with that. We see on your slide now that you have a company called Sirocco, and I know that there's a story behind that. Can you describe some of the challenges you identified with Sirocco and the journey to solution?
Yeah, absolutely. The company Sirocco, they make these air dryers, and they approached us around 1.5 years ago because they have basically a rather complex, massive part that's around 130 millimeters in height, if I'm not mistaken, which was intended to be placed outside in the outside environment on these road dryers. And they were typically milling them out. So they were doing subtractive manufacturing to them. And they came with a slab design that, we managed to print. And after I printed one of them, I actually asked the CEO of the company, Brian, I mean, why are we printing this thing? I don't really know what it is, right? And then he said, it's a battery holder. So then I looked back at him and I said, so it doesn't have to hold weight, you're basically saying. It just has to protect it from rain. And he said, yeah. I said, great. Then I climbed on top of it and I showed him, well, it can take my weight. So why is it so thick? And he said, well, the CNC guys told us that the minimum wall thickness should be this much. And so I said, well, hold my beer. Let me optimize this for design for additive manufacturing. So we ended up with a material reduction of over 40%, which meant a cheaper cost for him. He ended up ordering 18 pieces and faster printing time for us. and overall just inoculating this idea that design for additive manufacturing is paramount. And yeah, those devices, those battery holders, they exist today on their devices. So it was a win-win, I think, for us and them.
Super interesting. So to sum up, please tell us about what you think regarding the ease of use of the machine, all the way from the part preparation to unpacking and support removal. Basically, how it is to operate the machine, change powders, and so on.
Yeah, so I mean, I have no problem with that because I have a lab engineer that does it. But I think, no, I'm also trained on the machine and I have also done it myself plenty of times. I mean, I can highlight one thing to put everything else into perspective. There are days in which in the morning we print copper and in the afternoon we print steel. And I dare you to find another manufacturer of this quality that can facilitate machines that do this. Regarding the preparation, I mean, it's slicing, and Xact Metal is integrated within Magix, so they have their own module in that. So you can do, not only do you get to use Magix, you get to benefit from the support from Xact Metal. I mean, we talked to Eric, their programming guy, and asked him, hey, can we maybe disable these checks and do these weird things with boundaries once in a while? And he basically tells us how to do it, which I love. Again, you don't need to do it if you just want to print, but for me, this is paramount. But regarding handling powders, of course, we have the PPE and we have all the precautions needed for this. But I mean, this is not in any way something that anybody should be afraid of. You should take all the precautions and, by God, you know, in the beginning, do it slowly. But we don't. I mean, this machine runs for us 24/7 basically. We started with me and Oljerd, my lab engineer, using it. Now I have 2 dedicated teaching assistants, student assistants that use it. So they take a day basically to be trained on the machine, and that's it.
Great. Any final notes or things you want to say to the audience if they want to get started? Anything to add?
Yeah, I mean, I think given my experience with Xact Metal and Protech, I think you should not let these guys go unchallenged because they are very, very good partners in developing stuff. So I don't like to, you know, take things as they are without questioning them a little bit. It's just the kind of guy I am, I guess. But I find that if you go for a system where you think that you want a slow and steady yet firm handheld approach in the beginning, these guys are willing to offer you the support. I mean, I have 50 companies I work with on a regular basis at different levels, right? And the way we work with Protech and Xact Metal is unparalleled, and I can say that wholeheartedly. I mean, there's nothing that we ever approached them with that we were not. I mean, maybe we got a no, but it was not a no in terms of we can't do this. It was a no, we don't know how to do it yet. Give us a week and we'll figure it out. So if you do go for this system, which I really think makes sense, especially in an educational setup, given the price and given the ease of use and the robustness of the machine, I think that you should really view these guys as partners because they will help you tremendously much more on the way than I feel other manufacturers would.
Thank you for all the kind words and the very interesting presentation, Andrei. I think
Thank
it's
you so much.
Back to you, Anders.
Thank you. Thank you. Just a short presentation of the local team here at Protech. So if you're based in the Nordics and you want to talk to us, you talk to me in Sweden and you talk to Thomas.
Yeah, if you have any questions or anything related to Xact, then, and you're in Denmark, please approach me. On to you, Jari.
Yes, hello. I'm Jari Laine from Protech's Finnish office, and I'm responsible about Xact Metal sales in Finland. That's briefly. So over to you, Terje.
You are muted, Terje.
Well, there you go, Terje.
It should work now, Terje.
Now you can.
Thank you. Hello, I'm Terje from Norway, placed in Moss in the middle of Oslofjord, and yeah, the country manager for Norway. Do everything here. Thank you.
Thank you, Terje. And now we go over to the Q&A session, I guess. We do, okay. Do we have any questions for Andrei? Yeah, either you raise your hand and we'll make sure that you get a possibility to talk directly with the mic, or you can type in a question in the chat. Any questions? Everybody is
Everyone
probably
is
very shy.
or blown away, amazed.
Yeah. Yeah, the presentation was so good, Andrei, that there are no questions. Yeah, I know it's hard. It's sometimes, well, difficult to ask questions in a large group, but we are all friends here. So if you have any, just raise your hand.
I think that also, if there are questions outside the experience, I mean, I also can give you a lot more technical insights into this. So
Good.
anything that could strike your curiosity, just ask away.
Yeah, then I'll start with my curiosity, because it's huge when it comes to your activities. What is the next material on your list? What do you want to print?
Oh my goodness, I might have to kill you if I tell you, but
no, you can't. You're not allowed to kill me.
No. So we are basically, I've been at MIT a couple of weeks ago to talk about, I would participate in a workshop for reactive fusion and additive manufacturing, and we will continue very much looking at materials that are usable in a fusion context, so something that's not highly neutron activated. So we're going to continue with our coppers, but also move towards printing GR-COP, this copper chromium niobium alloy, which is basically, it's a NASA alloy made for aerospace applications, and we want to master it so that we can use it for external low neutron activated parts. So basically, we're going to continue on these reflective metals. That's one of the things.
Is that one of the copper alloys that have a heat deep? I don't know the English word for it. Heat conductivity that is very similar to pure copper.
Absolutely. So basically, the reason you have it in this form is that this formulation is that the chromium allows it to be printed, and what you have in the niobium is basically something that allows it to go very high in temperature, but also it gives it a good stability at certain temperatures, so structurally. So it's formulated to hold 3,000 degrees and this type of thing.
Okay. I think we have some questions. Yeah.
I have a question from the chat. It's from Gorgon. I'm curious on figuring out the parameters. For your information, I'm not too familiar with what those parameters mean, but could you not AI them? What I mean is to guess them with computers, or does that just imply you need to have a good simulator for the material?
Yeah, I think I can answer that. Or I can attempt to answer it. So thank you for the question, Gorgon. It's definitely a very interesting and deep topic. The short answer is, of course, you can use AI for it. And the mid answer is, of course, we are using some form of processing for it. The problem is you don't really want to print 100 variations and then see what really works. So rather, the trend in research and the trend we are following as well is you want to predict what the material parameters would be. So the combinations of laser speed, hatch distance, spot size, and all this. And there's a lot of literature that suggests different things, but you're very right. There's no go-to simulator commercially available or whatnot that can tell you that this is going to work. Try it first try, whatever. There are steps towards this, absolutely, but you still need to do the raw work on having these parts made. What's also interesting, except for the predictive thing, is the monitoring. So we are also applying now for funding, and we are probably very close to get it, in terms of investigating how the melt pool behaves during print. So there's in situ monitoring that can be done with a variety of ways. You can basically use the refracting part and the reflecting and the refracting part from the laser to monitor how the heat is basically building once you're melting these powders. You can also do, I've seen some crazy stuff in literature with electromagnetic signals, basically the footprint you get. So how does this thing actually sound and how does it vibrate while the melting occurs? And that gives you that gives you an idea for this research gap, basically. So yeah, the short answer is that you can use AI to process it, but it's not really AI. It's more of a, quick algorithm that can quickly see what parameters are good, but you still need to perform tests. You still need to characterize them for density. You need to characterize them for strength. You need to characterize them for continuity. You can have a very dense part that has one crack through the middle. It's still a useless part, right? Or you can have a part which is rather porous, but has the pores very well distributed, which is, maybe better. I hope that answers the question to a certain extent.
Thank you. We have another question.
Thomas, before you read the question, there were 2 hands raised to ask a question directly and not in the chat, but they took down their hands. So
yeah, one of them wrote the question in the chat.
Okay, but if you want to, again, please raise your hand again, and we'll make sure that you get the mic. Let's take the chat questions first.
Okay, we have a question from Hassan, and that is, do you have any suggestions on using simulation software to simulate the printing and reduce the printing failures?
Yeah, I mean, there are commercially available software out there, depending on what you are into, I guess. Do you want to optimize for time? Do you want to optimize for cost? Do you want to optimize for other things? You can use Ansys. Ansys has a built-in module for this, and they have had it for a couple of years now. I will say that they are limited in terms of what you can expect for complex geometries, because think of it this way. If you print an object, I don't know, I have some WD-40 on my desk because why not? If you print an object and you have your build plate here, if the object grows in this direction, by the time it's at this point, you have a very different thermal gradient occurring here than you did when the object was this tall. So not only do you need to account for the parameters and the optimization for that specific material, you also need to account for the geometry. And let's make it worse. Let's say you have a geometry here that's very tiny and curls downwards. Then you need to adjust for that. So to give you the straight answer, you can get away with a lot, perhaps with commercially available software. But in the end, it's really these home-cooked Python models that really predict to a certain degree better. So yeah, there is work done in this in literature, but it's far from being complete.
Yeah. Thank you, Andrei. There's a follow-up question to that. In your printing experience throughout the years, how much steep the angle against the recoder?
It's a question of what the geometry is. If I print a rectangle, I mean, the golden rule is somewhere between 30 and 45 degrees, right? If you print a very thin pin-like structure against the recoder, there's a very good chance that it's going to curl up, right? No. So that's the beauty and the drawback of 3D printing in general, right? There's no one-size-fits-all answer to stuff. But if you have an actual plate, so if you have a cross-section similar to my phone, you will probably not print it this way. You would orient it 30 to 45 degrees.
Yeah. Did we have a question directly with the hand raised, or?
Yeah, it was lowered. So
okay.
Keep on going in the chat, and we'll see if it's raised again. So.
Okay, this is a question from Matthew. What are a couple of key features you believe are the best aspects of Xact Metal 3D printers for utilization within universities, or more simple, why Xact Metal over another metal 3D printer?
Yeah, that's a very good question, Matthew. Thank you. So our experience was that we did not want to risk buying a system that is plug in or press a button and something comes out of it, because we are very interested in, as I said, tweaking and doing things in in a very tailored application-specific regime, right? So the reason we got Xact Metal and not a 3D Systems machine or an EOS machine was actually not because we couldn't afford it. We had the budget to get one of the much higher priced service equipment. But we went for this because it's just much, much faster to change materials in between. It's far less costly to change material in between. And the open powder system is just tremendously good for us because we can do pretty much anything we want with the powders, and the open parameters also allow us to tweak things. So I think for a research center or an educational context where you can afford and you should afford to play around with things, this is the type of platform you want. Are there advantages to EOS and 3D Systems? Sure, there are. If you want to manufacture at scale and you really want repeatability and you want to print large volumes and whatnot, that's the way to go. But if you want to tweak this, tailor to your application, and don't, not spend a ton of money to change materials or a ton of time either, I think this is the great flexibility of this system that make us be very happy with our choice in the end.
Great, thank you. Any other questions?
Is there one in the chat, I think?
No.
Yeah, there's one in the chat.
Yeah, no, there's one more. Okay, this is from Jose, and he says, what are some key design considerations or best practices for creating parts specifically for 3D metal printing, referring to the battery holder, for example?
Yeah, so again, it depends on what you want to get out, but you can absolutely go by, well, since I can use 3D printing to enter a virtually limitless design space, right? Can I use the least amount of material I need for this? Can I optimize the shape for design for additive manufacturing, right? So then you think about, should you maybe decrease the wall thickness to the, let's say, 1 millimeter, so that you can save this material? But then the next question is, if you build something that's very thin and tall, the thermal gradient up here might mean that, well, it's probably going to delaminate in that area. So the design considerations are always, always, always linked to temperature. Everything that happens inside that chamber while you're printing is a function of temperature. The way you dissipate this heat from the shape down to the build plate is dependent on the supports you generate. So that's actually the art of metal 3D printing, if you ask me. The part itself is cool enough. What do you do with the supports? How can you actually tailor the supports to structurally support your part, but also dissipate the heat in a meaningful fashion, and then also be able to remove them afterwards? That's where the art really comes. So the best practices are, yeah, avoid, as with any kind of printing, overhangs, because then you don't need supports. But generally, use the machine to what it can do, and that's minimize the material.
Thank you. Any other questions?
We seem to have no questions in the chat and no raised hands. I will ask one question so that everybody gets a chance to think if they have any more questions to you, Andrei. You were talking about the recoater and the angle towards the recoater. I'm assuming now that you have some experience with other metal 3D printers, powder bed fusion with recoaters. Do you see a significant difference in terms of Xact Metal's approach of using a soft recoater compared to some of the other systems that are using harder recoaters? You see differences there, or?
Yeah, I mean, one obvious difference is that the soft recoater needs replacing more often than the hard recoater. However, it's a very cheap consumable. It does mean that in case you are in doubt that the recoating is done well, you have a go-to place to approach the problem from. You just open the thing and it's very fast to do. Quality-wise, of course, if you forget to replace the recoater and it starts getting damaged because it's obviously soft and it's in a 100-degree environment, then you might, of course, risk having bad recoating. So that's something to consider for sure. But for us, I mean, we just think that, okay, every 2 or 3 prints, we don't replace the recoater, we just look at the recoater And it very often is that we use the same recorder for, I don't know, 2 weeks, something like that.
But do you see the recorder, the soft recorder, as a sort of a mechanism in the machine that results in lesser crashes than a hard recorder would, or is it that you create parts with so much sort of support that you are sure that you won't get any parts racing up and therefore not crashing into the recorder?
Oh no, I mean, if you return to this large copper part we made, it consistently had bulges. There were bulges that did not prevent the printing to succeed in the end, but that's exactly because of the soft recoding. So we could tolerate a little bit more in the journal. So it's more fault tolerant in that sense.
Yeah. So in those cases, it was more tolerant. Well, the design with soft recorder is more tolerant, which means that you have a higher chance of actually getting a part out of your print rather than a crash.
Absolutely. And it can mean that the print is maybe not ideal, but I would rather take a part which is 99% dense instead of 99.1% dense, and it still works. I mean, it still exists. So.
Okay, I don't think we have any more in the chat, and we don't have any raised hands. No?
There is one in the chat now.
Yeah, that's one. And that's a question from Hassan again. Did you try to put a custom recorder that you made?
So if you're talking about the blade itself, the recorder bulb, we actually have tried just for fun to 3D print it in silicon resin. And we didn't spend much effort into it. So we printed with it, and it would work for X amount of time, but the problem is we printed in a resin that would not hold the heat very well. So, we were like, okay, this is something we can probably look into sometime when we have time, and we never do have time. But we even tried making our own blade, right? And of course, you can get the one prefabricated, and it's the one that fits the design. But in the end, it just has to be something whose viscosity versus the stiffness is in this golden part that's, it's soft enough not to jam, but it's also stiff enough to not, attract the powder and get it stuck in. So yeah, you can actually make your own recoated bulbs. But again, they're so cheap that you don't really consider it.
Good.
Okay.
I think we're getting to the end of the webinar. Therese, am I right that we will distribute the recording to all that have participated or applied for the webinar?
Yes, that's correct.
Good. Then I think we leave it at this. Thank you, Andrei, for a very good presentation. Much applied, and hope that has given all the participants some good news or good information about metal 3D printing and the real stuff, not the brochure stuff.
Yeah.
So,
thank you for having me.
Yeah, you're welcome. Thank you, everybody.
Thank you.
Cheers.
Thank you.
Bye-bye.
Have a good one. Bye.